Let me just remind you a little bit of what I concluded with last time. So there's going to be some more abstract, a little bit more abstract thing before I get to toric varieties, but it's going to be very simple now, and I hope it's going to make things clearer. So we just said the action of, to make it more precise, of T locally trivialized action on the category C is captured by a fibration of C over T check, or as the structure on C of a module category over a tensor category of coherent sheaves on T check. So it means I know what it means to tensor objects in C with coherent sheaves, but it's useful to think that you're sheafifying C over T check in a way which makes it linear over the structure sheaf. That's what's happening.
Is that the same as just being linear over functions on T check?
Yeah, because if it's co-limit closed, that's right, which I've been assuming, yes. That's correct. Because that's all we have, actually. We have an action of the ring to begin with. So the rest comes from resolving modules. All right, so let me spell out in a more down to earth, more familiar terms, or more familiar looking terms, what this does. And for that, maybe one example, last example coming from pure algebra for a while, one example would be useful. So let's look at an example of a locally trivialized torus action. And we're going to take the category of finite dimensional representation of the Lie algebra of the torus. Because at finite dimension, there's no problem exponentiating them to the whole vector space as a group, right? Now, we know this category can be sheafified, can be spread out over the spectrum T star, a set of eigenvalues of the Lie algebra. The irreducible corresponds exactly to points in C star, of course, the characters. And you can say more specifically that this category C is equivalent to the category of coherent sheaves on T star with finite support, because of finite dimensionality. Now T star dual Lie algebra maps the dual torus, so certainly you get an action of coherent sheaves on T check on the category C. Therefore, the original category C must have an interesting action, locally trivialized action of the torus, because it has this interesting fibration, interesting map to T check. And here's the action. The action of the group does nothing. But in addition to an action of the group, the functors, I have to supply a trivialization near the identity. Now the functor itself was already trivial, was the identity, and now I have to trivialize it again, so I have to specify an automorphism of the identity functor, depending on a point in the torus, provided I've been able to write it, to lift it to the Lie algebra, or if it was near the identity, if you prefer. And I'm going to declare that this trivialization is simply the action of the exponential of psi on each representation. Remember, every object in the category was a representation of the Lie algebra. So all the information here is a trivialization, none of it is in the action of the group. If you forget about trivialization, it's a trivial representation. So the vibration to T check that we discussed looks awfully analogous to the spectral decomposition of a vector space under a set of commuting operators. It's like spreading it over eigenvalues. Now at first you might think that the true spectrum we're looking at should be T star, what we started, and not T check. But that's not quite true, and because if you have the patience to go to the definitions, for every integral character, for every character which extends one of the torus, tensoring with that representation of the torus gives an automorphism of the category C which commutes with the group action. So really, this category, by allowing all representations of T star, contains sort of something like many copies of the regular representation of T mod T log. It has this translation automorphism which, if you like, we can break it up into copies of itself, or rather commute with the action. So let's write last diagram I write for a while, promise. All right. So what do we want? We want the commutation of the group action composed with tensoring. So an isomorphism group action composed with tensoring, the tensoring composed with group action. And I'm choosing to write as an action on each representation, just scalar multiplication by t to the mu. So t is the point, the torus, mu is the character I chose. So it's going to be an automorphism on each object. And we have to check this commutes with all the data, and there was a trivialization data here, and indeed it does, because the trivialization data is relating this to the identity. So down here I'm writing the identity automorphism from 1 to 1. Here I'm writing this non-trivial automorphism I've just put in, and here I had trivialization automorphism, and I've chosen things so that they commute. And notice you could not do this if mu is a non-integral character, because you need to be able to define a sub t for every group element t up here, not for a Lie algebra element, to be able to get this to square up. So translation by a tensoring with a character of the Lie algebra is not going to give an automorphism, not going to commute with the group action unless it was an integral character. So really the space of characters is t check. So the moral of the story is, let's go back to vector space for a second. If you have a B-model representation of T on a vector space, you can find a spectral decomposition into one-dimensional representation, and they're classified by points in the Pontryagin dual group, which has the cohomological interpretation as H2 of group cohomology, topological group cohomology with integer coefficients, or continuous cohomology with O star coefficients, with coefficients in C star by the topology. For categories, what we're finding is an analogous picture where the representations of T have a spectral decomposition from the action of the coherent sheaves on T check, parametrized by points in Langlands dual torus, and that also has a cohomological interpretation as second cohomology of the classifying space with C star coefficients. And this is the classifying space of T modulo T hat. David Benz-V would prefer T hat. And the last group classifies the action of T mod T hat on vec, this last cohomology group. I mentioned that last time. So again, we've decomposed the category into like one-dimensional isotypicals by spreading it out over its spectrum. And you could summarize it by saying that the categorified Pontryagin dual of this group T mod T loc, locally trivialized action, is the Langlands dual torus. So by categorifying and also making this change, we've moved from the weights of T to points in the dual torus. This actually is a well-known point of view. This is not a dramatic discovery or anything, but it's a good way to think about what I just said. Okay, so armed with this insight, we can now make a good guess about what how to compute the fixed point category. Geometrically, well, okay, now we can even see the guess. Namely, if you look at the skyscraper category supported at 1 in T check, that is the analog of a trivial representation of the group T mod T log. That is the category vect on which the category of coherent sheaves acts trivially, acts by the fiber at 1. So in fact, a sheaf here acts on a vector space by tensoring the vector space with a fiber of S at 1. That's the definition of a skyscraper category at 1. So based on that, it's reasonable to guess the fixed point category is a version of the fiber of C over 1. So for example, if C was a coherent sheaves on a complex manifold mapping to T check here, then the fixed point category should be the subcategory of sheaves supported on the scheme theoretic fiber over 1. And that can actually be justified. A precise version of this statement exists. There exists also a precise version of a derived statement, and for that we need to look at the work of Benz-V, Francis, and Nadler, defining tensor products of categories and Hom of categories over tensor categories. And this can be done, and it gives the expected answers. Indeed, if the categories were sheaves on complex manifolds, you are taking fibers in the way you expected. So this insight is essentially correct, can be made precise, with a huge provision, and the provision is forced upon us by physicists. And actually it's forced upon us by the fact that soon we'll be collapsing the grading mod 2, and that's already happening in the Fukaya category. Oops. So if we're staying in the Z-grade world, this would be essentially the story will be made precise. And we'll see that in the Z2 grade world, this is not true. So LB. So I'm done with this kind of stuff for the moment. Any questions so far? Going to an toric example.
But you're not going to say more about this provision enforcement?
Yes, but probably not in the remaining 45 minutes, because I'd like to show that it actually applies to something real. But yes, I mean, we have to discuss homological algebra mode 2 and the uncompleted Hochschild homology and that sort of thing at some point. And actually what we're running into, I'm giving the game away, we're going to be running into Kapustin's version of the Rozhansky-Witten theory of a holomorphic symplectic manifold. That's what's going to control what's happening, which is exactly the tool that's needed, the delocalized homological algebra. Or uncompleted, even better. Okay, so then let me go back to a real-world example. I don't know. First, I mean, ignorance is a bliss. If I had known this example first and started from it, I would have run into the contradiction early on and I would have stopped. So, history played otherwise. I mean, I ran into the contradiction somewhere else, so I knew I was just doing something wrong. It wasn't a mistake. I had to fix it. It's a bit different. Okay, so let's start with toric variety for a torus which is C star to the n. And we know that's determined by its fan. That's a rational collection of rational polyhedral cones. They have disjoint interiors, they're convex, always forget that, and they meet along faces. And they live in the Lie algebra, so this is the Lie algebra of the torus. So this is a complete fan, it covers the Lie algebra. I've put in red the primitive vectors along each ray, and some nice theorems about toric geometry. Gives us a meaning of these guys. They correspond to toric Weil divisors. Torus invariant Weil divisors. You can get a fan from any polytope simply by taking convex polytope containing the origin by taking the cones over the faces. So, and conversely, if you have a fan, of course, you can choose a polytope. And as long as it's strict, meaning it really distinguishes adjacent cones, you don't happen to draw a straight line across, you get a fan as some sort of equivalence class of polytopes. There's more information in the polytope. So what can we say, just to recall? I'm sure everybody knows that except for me, basically. So each cone in the fan determines a monoid inside the lattice of characters of the torus. So it determines a ring among the ring of all functions on the torus, namely you're choosing the exponents that are non-negative on the cone. And spec of that ring is going to be an affine chart on the torus, and they're going to be glued in the way that cones meet along faces. And that's how you can build the toric variety by patching. And then the combinatorics of the fan translates into a lot of geometric properties. So for example, the fan covering the Lie algebra is equivalent to the variety being proper. The fan being integrally simplicial, meaning each cone is a simplex and it's the subset of lattice points inside is generated by those on the edges. That condition is equivalent to smoothness. And finally, the polytopes also have interpretations. Strictly compatible convex rational polytopes correspond kind of to ample line bundles. Let's be more precise. So ample line bundles in fact correspond to strictly convex integer valued piecewise linear functions phi on the support of the fan. The polytope is then defined by cutting off the place where the function is equal to 1. So it starts at 0, of course, in the center, it's linear, and then if you know its boundary where it reaches 1, then you know the function by linearity. And such a thing, which is integer valued on the lattice, of course, on n, not everywhere. If you have a polytope, you can define some sort of dual in the dual space called the polar. These are linear functionals which are no more than 1 on the polytope. And that also has a meaning. That's a moment map image of the variety for the torus action in the polarization defined by this line bundle up here. Actually, the variety itself bringing up moment maps to just GIT quotients and so on. The variety itself is a GIT quotient of a vector space. And that's a pretty standard way to do it. You can take it as a vector space, the vector space whose base is the rays, and the rays have primitive vectors along them that gives a homomorphism from this large torus E star to the R to the original torus T. It has a kernel K, and the toric variety is going to be the GIT quotient of this complex space under K, using again a polarization defined by phi. Polarization will just mean a character in this case of this torus. This function phi has some values on the edges which tell you the character. Never mind. Can wait. Remember Dennis Sullivan in a lecture actually taking the call. I won't try that. Alright. So here's an example I drew here about the only polytope I can draw, and it's polar, I think. It's probably related to the only threefold I know. But, alright. Okay, so from this data we can define something much more sophisticated, a mirror. The mirror is going to be a complex manifold together with a function on it. Oh, right. Yeah, I have two places where I can check. I don't know why I keep looking back. But, so the complex manifold, I'm going to take it as sub-manifold of a dual torus T check. And it's going to be the compact part tensored with the exponential of the dual polytope, but actually I should have said it's a translate of it. I should really read for it the image of the moment map. Algebraic geometries, of course, don't do that because there's no longer an algebraic variety. You cut it off like that and just take the whole complex torus as a mirror. Differential geometers prefer, coming from special Lagrangian geometry, prefer to keep that in mind, and I think it's a bit of an unsettled issue which one is best to consider the mirror. But this makes sense from a point of view about to see in a second. And on this there is a function, a sum of Fourier modes with coefficients qj. And the function is just the sum of the Fourier modes come from a primitive rays. Remember, those were co-characters of T, therefore they're characters on T check. And these numbers Q, they're Novikov coordinates actually. The real part comes from the Kähler class. It's the exponential of phi of rho j. And their phase represents a B field on X. That's how I understand people think about the mirror. I'm not sure the B field is doing the Fukaya category, but that's how you want to read the Novikov coefficient. And for... why do we need this fact? I think it's a true fact. If X is complete, then H upper 2 is a quotient of... naturally a quotient of R. Completely forgot why I need this fact. All right. So algebraic geometers, as I said, like to take the entire torus, so we have something algebraic, but there are GIT restrictions to restrict to this slightly smaller cutoff piece. So part of the claim that this is a mirror is that the Fukaya category of the original X is equivalent to the matrix factorization category of its X check with for the function W. Now, certainly, matrix factorization of W over X check can be tensored with coherent sheaves or vector bundles on T check. So this category is naturally a module category under coherent sheaves on T check, simply from the projecting the torus and forgetting W. And this captures the action of the compact torus on the Fukaya category of the original. That's at least maybe enhanced mirror symmetry conjecture statement. All right. So in fact, one can derive this construction of the mirror from just one thing. We can derive it in many ways actually, but from just one thing in terms of group actions. Namely from our ansatz, our guesses for the fixed point category, and knowing the mirror of a vector space C to the R. All right. So I'm going to claim, in fact that's following the rules basically, the mirror of C to the R is going to be the dual torus. I'm not bothering to cut it off, although we could, with potential just the sum of the coordinate functions. And the action of the big torus C star to the R in the Fukaya category is, as before, encoded by the projection to C star to the R, just the identity map, so for getting the potential. And the action of the sub torus K, so there was an exact sequence somewhere. Things keep disappearing, it's amazing. I could swear there was an exact, oh here. Right, C to the R maps to T and the kernel is K. So we're going to mod out by K and something will be left over the T action, which will be our toric variety. So we want to know how to mod out by K. And the action of K on the category is then captured by the projection from this C star to the R dual to K dual. And we just claimed boldly that the fixed point category is the fiber of the category over the point 1 in K check. But the fiber over one of its projections is a dual torus T check with a restricted W. And this, where is it? Gone. Unbelievable. The restricted W essentially these are the coordinate function on the CR that projects to the variety basically. And you can think, if you like, that the rays in the fans are the mapped images of a coordinate axis in C star to the R. That's a consistent picture.
Sorry, so is that the ansatz is sort of the claim that
The ansatz, the fixed point category is the restriction of this. That's right. The Fukaya category of the quotient is a restriction, the fiber over 1. And that's just the mirror I had written previously. I just left out Novikov coefficients here. You'd have to put them in, of course. They depend on the choice of the line bundle, which is reflected in the torus action only this time. Now, what was the story about the restriction to not taking the whole torus, but taking the moment map image inside? Well, what that does, it'll guarantee that the fiber of this projection to K check is empty when the GIT quotient is empty. So it sounds nice that when you get an empty quotient, you get the zero category. There's nothing there. But since we're meant to get the gauged category and maybe not quite the GIT quotient, it's not completely clear it's a virtue or a vice. That part may need attention. I mean, I haven't been able to determine that yet. So, no, of course, determining it would tell you which one is really the mirror, the cutoff torus or the entire thing. It's reasonable to vote for the cutoff one simply because this other one I really lost information, so it doesn't sound right. I should point out there's nothing new here either. This was the original derivation of the mirror construction by Gibenthal, Hori, Waffer, but of course they didn't talk about categories and fixed points, they talked about other things. So, but we start with CR and then restrict to some fibers of some map. That's was the construction. Now, time for the confession. There's a major problem with this picture. I mean, it sounds wonderful, doesn't it? But it sounds wonderful because I haven't told you what the matrix factorization category is. So one of the properties of matrix factorization category is that it is supported at the critical points of the potential W. Now, as you can see this function, it has no critical points. Therefore, the category up there was 0. And I'm taking a fixed point category and I'm getting something definitely not 0. Now this is a linear functor, and we tell students in linear algebra that a linear map takes 0 to 0. I put that on the exam almost every year. And we'd like to preserve that properties. I mean, there's a problem. So there's an easy cop-out, not a real answer, which says, well, the category isn't really zero, just equivalent to zero, and that equivalent is not equivariant enough for the torus action. And that's why there is a fixed point category. And to some extent, that's true. But that's not quite what is happening. And to understand what's happening, I think I have a picture of what's happening. It's a geometric picture of what's happening mapping this. And it's not happening in the torus T-check, but in the cotangent bundle. And it doesn't involve points, but holomorphic Lagrangians. And it leads us to see, I think, this category in a completely new light. It relies on the fact that the grading has disappeared, only survives mod 2. That's why there is a global object. And once you adopt this perspective, you can see much more. It's amazing. It's like you were blind, but now you can see. The price to pay is that we're going to see double. Everything that geometry computes is a double of what you would like to know. So we need more information, the geometric shadow. That's because geometric shadow that we're seeing, the cotangent bundle, well, will double in a way the torus, is going to be essentially a Hochschild cohomology functor. And that's like a doubling. Where vector space literally replaces it with its endomorphic matrix algebra, for example. So I think maybe it's a point to pause and stop for questions, and I'll begin to explain this homological algebra story. But
sorry, I will explain why we look at the matrix factorization category.
oh, should I explain the matrix factorization category? I can do that. It doesn't take long to say 3 words about that. Yes. In fact, I didn't mean to and forgot. Yes. Thank you. Any other questions?
This statement that W has no critical points, is that somehow mirror to the absence of, say, exact Lagrangians in Euclidean space, or Duality?
Yes, but I think right. I mean, you can. Okay, so there are lots of things I don't know, but one way to write that mirror, you can do it from the SYZ picture. Just take as your Lagrangians a torus, and then look to check to see if it's obstructed, and it is. There are holomorphic disks ending on it, and they give you that formula for the potential. There's no critical points, and that's why you're out of luck, more or less. But I don't know if that answers your question, really. But I mean, I don't. I mean, I see the problem coming from. Yeah, from the potential, from the holomorphic disks crossing the anticanonical divisor, kind of. That's the only way I understand it. Of course, guessing that is the only Lagrangian you should take, and therefore that's a valid model for the Foucault category, is just a guess, like many others. So, you know, yes.
Is there some principle that says that if I take a Foucault category of the, so I have a torus action, I mean, if I take Foucault category of the quotient stack and of the GIT quotient, should they be the, I mean
yeah, that's a very good question you're asking. That's right, because I'd like to say, because we're taking a fixed point category, in fact, a derived fixed point category should correspond in some way to the stack.
Right.
But the counter reply to that the stack is not a very natural object in symplectic geometry. The stack is natural on the algebraic side. This should happen on the symplectic side. And the only kind of quotient we know how to build on the symplectic side is the GIT quotient. So that would be, I think that's exactly what a symplectic geometer told me. So I should not expect anything other than the GIT quotient to show up. I'm a little bit uncertain, because I can certainly know examples where I can rig the GIT quotient to be 0, but compute non-zero invariance from the gauged category, which is a little.
Situations where I know my Foucault category is something like D modulus, then I know I will get the answer on the stack, right? So maybe there you have some vanishing.
Right. So of course, when you take something like, if you just say D modulus and they're not integrable, remember this story doesn't apply so well anymore. I've assumed that the trivialization was integrable, and that makes a huge difference. I mean, a lot of things simplify. For example, in this setting, it's easy to prove the reduction of the maximal torus in the Weil group. If you understand the normalizer of T and G, you understand the G action. There's no more information. And that would be completely false if you were in a D module setting, say. So yes, I don't think I've made up my mind about that, but I mean, if I'll be happy to hear any views on it. All right, the first question was matrix factorizations. And I think the most accessible reference I know is the paper by Orlov, but I forgot the title. It may have matrix factorization in the title, if not in the abstract. So we're going to be on X a smooth manifold, and W from X to C a holomorphic function. Some things are a bit easier if the critical locus of W is compact, which would kind of force it to be isolate W to have isolated critical points, and then you have to worry a bit less about finiteness. But there is a theory even without for non-isolated critical points. And let's define a matrix factorization. Okay, I'm already jumped ahead. So let's just focus on one critical point of W. So choose a critical point X and shift W to make W of X is 0, and then a matrix factorization is a pair of projective modules, projective OX modules, together with a pair of maps. Let's call them P and Q. These are all modular maps, such that PQ and QP are both equal to multiplication by W. And you could think of it, if you like, as a two-periodic thing, but it would not be a complex because the square of a differential is not 0, it's W. But you notice that HOM of two matrix factorization defined in a rather obvious way, so P1, Q1, P2, Q2 is a differential vector space, is a complex. Essentially because it will be taking commutator with W when computing the square, not multiplication by W. So you can see that this even makes sense in a non-commutative setting if provided W was central. So you define the derived category of matrix factorizations.
What's it got to do with the point X?
At the point X, W had definite value, and I had to shift so that it was 0. So if you want a different point, you have to shift.
That was all thing X.
That was the point little x. Which X are we talking about? Sorry.
The projective are over the map, right?
Projective modules over X, but they only matter in the neighborhood of a point little x. They only matter in the neighborhood of the critical locus, to be honest, in general.
Yeah, they're not vector spaces. Are they? That's not.
Yes, OX modules. Yes. So what do you mean they're not vector spaces?
It's big
Is the question whether this is O little x or O big X?
Yes.
This is good enough.
What's that?
That's good enough. They can be defined locally. The category will be supported there. Well, at least in this definition, good enough. The derived category of matrix factorizations.
Doesn't mean this can't be vector space. I'm sure it's the term.
Yeah.
There seems to be an issue, but it seems to have been resolved without my input, which is how everything should happen in an ideal world. Factorization has as objects the things above, and HOM are going to be the original home modulo homotopies. There's a notion of homotopy which maybe I'll let you think about. Home is original homes modulo homotopies. And essentially, because these were projective modules, the valid definition of a derived category. You don't have to start with quasi-isomorphism and stuff. And the theorem which illustrates that, for example, everything lives in the neighborhood of the point little x. The theorem says that this derived category of the MF of W, MF of XW, maybe the one localized at X, is equivalent to the derived category of coherent sheaves on the fiber W inverse of 0, a fiber containing a singular point, a singular fiber, modulo derived category of perfect complexes on W inverse of 0, also called derived category of singularities. These are also, of course, the coherent sheaves which come from the ambient space. So you mod out by things coming from the ambient space and only keep the new stuff. And it's a relatively easy proposition that this is supported at X. You have to shift this value to make it 0, because if otherwise the composition is locally invertible, and that will make the maps null homotopic, so kill everything. It's kind of silly. Whereas in this definition on the right, somehow it doesn't matter. You could write that for every value, and if it's a regular value, of course, everything is a perfect complex, so you kill everything, but on singular fibers, you remember something near a singularity. There are many ways to think of that, but one way, abstract way, is to recall that. So what you notice here, this is now Z mod 2 graded. And there's a reason why it's Z mod 2 graded, is because the curvature has degree 0 instead of 2, the way curvatures ought to have. W is the curvature. It's the square of a differential. So, context maybe. The Hochschild cohomology of OX controls the deformation theory of OX as an algebra, as an associative algebra. So HH2 specifically controls deformation as an algebra. But the point of view which maybe was first pushed into mathematics by Kontsevich is that we should think Z2 graded, in this context at least, and think of all of HH, so HH1, for example, of OX, contains derivation. And HH3 would contain obstructions. That's a pattern. The rest of the stuff didn't have a particular, well, HH0 are Derby things somehow. The rest of the stuff didn't have a particularly clear interpretation until we started thinking about the infinity algebra, and Kontsevich pointed out that, well, you're allowed, it's okay to reduce the grading mod 2, and then all of HH even should give deformations. And all of HH odd should give infinitesimal automorphisms, or generalized derivations, if you like. And indeed, you can explicitly write from a cocycle, so from a cocycle in HH n cocycle, you can write a multiplication map from A to the n to A, but this ought to have degree, by the book, it ought to have degree 2 - n, 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 So 0 for degree 2. But so HH even from this point of view, unless n is 2, has a wrong degree, because A, the algebra OX doesn't have any grading to speak of to allow a co-cycle. Let's say we're talking locally. So, but if the grading is collapse mod 2, then in fact all the even MNs are acceptable as deformation. So all the even MNs, Mn as in A infinity multiplication.
What does that degree mean?
The degree, so this has degree 0, this has degree 0. So it's only correct if n is 2. Right? If A is degree 0. But if A was graded, then the requirement to have a Z-graded deformation, the Z-graded world would be at Mn should have degree 2 minus n with respect to the internal grading of A. Then you can construct a deformation, a Z-graded world. So all even Mn are allowed if grading collapses mod 2. Which leaves an interesting one, M0, which is a map from C to A, or an element W in A, and the co-cycle condition, in this case there's no negative Hochschild cohomology, is that W is central. So the higher M's define correction, higher multiplication, higher associativity rules, so you might wonder what you're going to make of an M0. It doesn't define any kind of multiplication. Well, M0 has to be interpreted exactly as a potential here and gives a deformation not of the algebra but of the category of modules. Of A modules. And it forms actually a derived category of A modules brutally after collapsing the grading mode 2. Let's do an easy example where things work as they should. So, what should I say? Good kid example. So the algebra A is now a differential grade algebra. How about the Ram forms on a manifold D? And W, a class, actually has to be a 2 co-cycle, omega 2 closed on X. So dW is 0, it's commutative, of course. So then that could be the curvature of something, and if it's an integral class, in fact it can be the curvature of a line bundle. So you can form curved modules over this A dot. These are going to be not complexes but graded vector spaces M with a differential, well, not a differential, what should I call it, with a connection with the property that delta squared is W. The whole thing is an omega xd module, and you want to be you really want to behave and put conditions like the one with your projectivity, so it must be perfect. So in the, let's just say perfect.
So what is the Hochschild cohomology?
The string topology thingy, so it's cohomology of x with coefficient the homology of omega x.
I mean, just to fit it in with your general discussion, right? This W is a class in HH0 event.
W is a class in A. Yes, already. And there was commutative. I think yes. W is a class in A, and A is commutative. So it's in the center. So naturally lift to the center. To HH2 of A. It's an HH2. Total degree 2. Hochschild degree 0, but total degree 2. Okay, so this time it has the right degree. That's why I said it's a good example, good kid example. perfect in thick closure of shifts of omega xt. And this category of modules actually depends rather dramatically on W. So in fact, even scaling W will change the category. Namely, if W is integral, so it's C1 of some line bundle L, then the operation of tensoring with L gives an isomorphism between the uncurved modules and curved modules. So whenever W passes through an integer value, I mean, you keep recovering the same category. When it's only a rational class, you could be lucky and still get a vector bundle with scalar curvature with Chern slope W. If it's not even rational, you probably cannot get anything in the category. So it's no, I'm sorry. You're still going to see the part of the homology of A on which this class vanishes. You might kill everything. Okay, I'm not sure if you kill everything or kill just a chunk of it, but definitely for generic W, this collapses quite a bit.
This category is connections with curvature W?
You can think of that bundles with connection to central curvature. That's what you're going to have, exactly. That's exactly what this tells you. Well, tensor with the RAM complex with differential form. The actual curved module would be the differential forms of values in the bundle, but yes, that's exactly. So it looks like a good kid example in the sense that, well, it's where it's supposed to be in degree 2, so it ought to be, in fact, it does give a Z-grade deformation of the category of modules. But you see actually has terrible behavior because scaling W changes the answer, whereas in this situation, scaling W does nothing to the answer on either side, right? You can just scale the maps to account for that. So the good news and bad news. Somehow because the scaling of W in that case can be undone by a degree scaling, so it's doing nothing. That's why scaling W does nothing. Whereas here, exactly in the range where, in fact, there's a moduli space in that direction. There's no linear obvious scaling structures. The moduli space is not a cone. Maybe that's a good way to say. Okay. So if you follow the HH2 directions in the deformations of the algebra, in those directions you can have a curved moduli space, actually. If you follow the other directions, I mean, just the grading makes it into a cone. So in the other directions, the generalized moduli space would have to be conical. So, seems uninteresting. Okay, where are we? Oh, we're 7 minutes from shut up time. So, any question about the matrix factorization category before I move on to try to explain how distinct points can intersect? Okay, so let's say we know that. So the lesson from here is we are forced to collapse the grading mod 2, and that's going to force us to change the way we think of homological algebra. In cohomology, we think that the grading makes classes nilpotent in some way. 1 plus x, if x has degree 2 or higher, is always invertible. You don't care about power series. But if you actually think that all the even things are reasonably things through spatial extension, then you would not be able to do such things. And here's sort of my spin on, well, before I give the broad picture, let's do some examples. And there's good news and bad news. It's going to be one category level down from what we really need. That depends. I mean. So we're going to be talking about algebras and modules, not sheaves of categories and tensor categories and things. So the other news is that we're going to use supermanifolds. So, and that's because in this dimension of algebra's modulus on Hochschild cohomology has odd generators. What you're adding to the algebra on computing Hochschild cohomology are the odd generators. So let's start with, let's say you're in a Cn or something, germ of a manifold X, and you have a point X, and here you have a skyscraper sheaf, let's call it Kx, K sub X, skyscraper module. What controls the deformations of that? Well, deformations are controlled by the derived endomorphism. Let me write it. Really, I should write R hom, a bit pretentious. R hom over OX of Kx with Kx. And specifically R hom 1. We're deforming a module as opposed to an algebra, so we're almost very low down level of Hochschild homology. Right? The degree has gone down too. So this controls deformations. And we can compute that, and it's actually exactly equal to the exterior algebra of the tangent space at the point X, the whole R hom. So Tx controls the deformations. And how do they deform? Well, you move the point in the tangent direction. Okay, not a mystery. But now let's try to follow the master and to do what Kontsevich was telling us. And this, we're supposed to look at all of the odd, in this case, odd part as a deformation space, as controlling deformations for this. So for example, if the dimension is 3, the volume form, so let's call it vol or something, in lambda 3 of Tx should give a deformation. And the great thing here, I can actually write down the deformation. So, but of course you have to write down this thing correctly. So we're not going to deform the vector space K itself. That would be pretty hard to see. We have to write a free resolution of that. So we resolve K by writing OX maps to KX, then OX tensor with T, then mapping to this is OX tensor lambda 2T and OX tensor lambda 3T, and now we're done. And the map at the point V in X, if you have chosen coordinates, I assume the map is simply contraction with that's why it doesn't work, because that's the actual resolution. The map is contraction with V everywhere, the vector V. So it vanishes linearly at X. If I write OX as a symmetric algebra, it becomes a Koszul resolution of K. Okay.
So V is in the tangent.
V, I've chosen coordinates, so V is now a vector. So this differential depends on a point V, which has been identified with a vector in the tangent space and acts by contraction.
So the exterior algebra, that's the whole of R-hom, or that's R-hom?
In the exterior algebra, this dot would be that dot, you're right, so R hom dot. Yes. Let me write this in case it's confusing. Let's do one dimension, so I don't have to write too much. The map would be OX to OX and resolves K at the point X, and the multiplication is by maybe V minus X, or V if the displacement vector is V minus X, if V is a coordinate, or V the displacement, however you want to write it. You can take X equals 0, this is getting complicated. Okay, that's multiplying by the coordinate. That's the resolution. And now, having written this complex, an obvious way to use a volume form to change things around, namely what prevents me from contracting from here all the way to there by the volume form. What prevents me is a degree, but now we agree to collapse at mod 2. So nothing prevents me. And then the new differential squares to 0 just as well, because odd classes anti-commute. Square to 0. So this new module, let's call it kx vol. How should we call it? It's a deformation of kx. But it hasn't moved the point. It's deformed without actually moving the point, or so it seems. Okay, something is moving. So, whoops.
Say what it is, I didn't get it. What did you do with the body form?
I just add the contraction operator going from here all the way to the end. Has degree 3. But 3 is 1 mod 2, so we're good. So it's a new complex. Okay. And if you want to check that it's new, you can actually compute. It's not hard to compute hom or r hom from the old kx to kx vol. And you'll see that you're going to get the exterior algebra of t. But because the differentials don't match anymore, it's exactly this discrepancy. It has a differential which is contraction with vol. So it will kill, if you like, the bottom and the top. So because this R home does not have agreed with the original, we know these two are different things. Really deformed it. Okay, it's shut up time. Should I kind of draw and continue for about to draw the picture of why this is actually moving, or should I leave a suspense?
Sure, no picture.
All right. So let me look at the following. So instead, let me tell you, this picture, everything we learn about schemes or so on is wrong. Okay, now I'm going to tell you the truth. Okay, okay, let's try again. So when passing to mod 2 deformations, in the picture of the speck of a ring and all the points in there does not capture everything. You can see it here because both of these are one-dimensional modules supported at x and they're different. And there's a nice picture which captures that, and I have to create Anton Kapustin with that because I probably would not have recognized it if I hadn't heard him discuss it in the context of Rosansky-Witten theory. So let's say Kapustin's of the Rosansky-Witten category. This is done one homological level down, one category level down.
Maybe we can move one level down.
Nope. So instead of looking just at X, let's look at its Hochschild cohomology. So X is an algebra over its own, let's say over a spec of Hochschild cohomology of X. So what X was an affine thing, affine and smooth. This is actually, according to Kontsevich, very strictly just OX, O tensor, the polyvector fields. As an algebra. And this has an odd degree -1 Poisson bracket, which is non-degenerate, so it corresponds to an odd degree 1 symplectic form, an odd symplectic manifold. So the spec of this is, of course, the cotangent bundle of X, but the cotangent bundle made odd. I'm not sure if there's a standard notation on it. Maybe let's call it pi of t. Cotangent bundle has degree -1. And it has an odd degree 1 symplectic form on it. And X sits inside as a Lagrangian, right? These are the odd directions. This is X, Lagrangian. And this is sort of spec of HH star of X. And that's the fundamental picture. X is a Lagrangian inside its Hochschild cohomology. So what happens from W is the volume form. There was a cubic function here on this manifold, at least if you trivialize choose coordinates. So you can, it's an odd function. Let's just remember even and odd. And let's use it as Hamiltonian to flow under a symplectic form. The symplectic form is also odd, so it results in an even flow. And if you apply this flow to a vertical fiber of the cotangent bundle, you're going to move quadratically away from it. Claiming that this guy here, the vertical fiber, is x over O of kk as a module, an algebra over h star of x, and this guy is x over O of k vol over as algebra, they're all algebras, over h star of x. And I should tell you, I have not used commutativity of x in this picture. The Hochschild cohomology is commutative by itself, so in principle this could be some sheaf of non-commutative algebra sitting over this Lagrangian in the Hochschild cohomology. And now you can see exactly this has moved. It's moved parabolically away from the vertical fiber. You can't get a straight notion because parity obstructs that. You can only make it tilt, but you can move parabolically. So now it's in principle possible to have two distinct points, deform them, and have their deformations intersect somewhere else, away from the zero section. Well, in this situation, this lower dimensional situation, that's not possible for a kind of silly reason. These directions are odd vertically, therefore they're nilpotent, so you can only see to finite order away from the zero section, so a point that's actually away will never materialize. But you can still detect it. That's a good homological algebra exercise to do once. You can detect this movement in the following way. How am I doing? 3 minutes, I think I'll be done. You can detect if you try the following thing. You let time flow. This is your x flowing in time. And you keep your skyscraper kx staying at x as usual. And take the other module coming in linearly into 0. And now you compute the intersection home between these two. And if this was kx as well, then the Lagrangian picture tells you that you're going to have two vertical planes coming in. They're going to intersect exactly at time 0 in a vertical line. And you're going to get the excess intersection, which is actually lambda 2 of the normal bundle to the travel direction, to the normal bundle of, so this is V, this is the travel direction, normal bundle of V. And the picture, as I said, is this is a path in the manifold. These are the Lagrangian spaces going with that. They intersect in the vertical. This is time 0. The vertical line at time 0. But now let's imagine that instead of this vertical plane, we're drawing the spectrum of the endomorphism ring, which is a parabola like this, and which gets shifted in time. So it's like a parabolic surface. Well, this surface intercepts the vertical plane at any time and meets it in a parabola. Of course, these points here don't exist. But right here at time 0, at the time of the intersection is a germ of a parabola. So at time 0, so the germ of a parabola, the quadratic germ, time 0. And the way you detect that, you compute x between this kx moving and this kx deformed moving. And it's going to be something of the same size, but this time t will act non-trivially. The first order. So the point arrives just a little bit before it should, infinitesimal. So if you're in a situation where these directions were even, and actually you could have points, you can see why now actually these disjoint points could have homes between them if you are measuring them in this context, if you were to globalize this Hochschild homology picture. So what I'll try to sketch out next time a bit is a cartoon version of this Kapustin-Rozansky-Witten picture in dimensions 2, and why that solves the problem of the empty category or the zero category becoming non-zero, because the category actually is not empty, it's not zero, it just lives somewhere different. It does not live in the zero section where we're looking, and the intersection happens elsewhere. So that's what I'm trying to explain. All right?
More questions? Okay, so we'll have a 10-minute break.